So we're looking at now partial derivatives. So let's start with just a brief discussion of derivatives and maybe their connection to a partial derivative. So given a function f of x, there is a single independent variable, and when I look at my graph here, I see it along the x-axis. That's my independent variable. There's a single independent variable, so the function changes as I change values of x. So, for example, the function that's pictured there is f of x equals x cubed minus x. And so we might ask ourselves, how can we interpret the quantity f prime at 1? In other words, what does f prime at 1 mean? What does it mean? So, well, we could have a procedural kind of perspective on this. And if I had a procedural perspective, I would say basically I'm going to replace x with 1 in the f prime of x function. Okay, so very much a procedure. How do I actually write it? How do I find it? That would be how I would find it. Okay, that doesn't give me much meaning. It tells me how to compute it, if you will, but it doesn't tell me what it actually means. So I could expand on that a little bit. Instead of having just a procedural, I could think of, well, maybe f of x is a position function. Then that would give some meaning to f prime at 1. That would mean this is the velocity at t equal 1. More generically, I could say that it's the rate of change at x equals 1. F prime at 1 is rate of change at t equals 1. I could also say it's the slope of the curve at x equals 1. I could also say it's the change in y over the change in x at x equals 1. So the point here is that there's many interpretations, if you will, of what f prime at 1 actually means. And so which one of these meanings or interpretations we choose to use really depends on the context in which we are actually looking at a derivative. Now, so that's how it works with, or how we think about things when we have a single variable. Now let's go ahead and look at what happens if I happen to have two variables. So there's two independent variables. So function values change as both x and y change. Okay, so my output can change based on a change that I made in one of my two inputs. So what we do is we consider how these changes occur independent of each other. So I don't want to, if I'm thinking about rate of change, I don't want to necessarily allow them both to change at the same time or simultaneously, because then I cannot track how the output changed based on the change of the inputs, because I was changing too many things at one time. So here's how we kind of think about this. So if I'm given a function of x and y at a point, some point in the xy plane, so we'll say x naught, y naught, this is a fixed point, what we can do is we can consider the rate of change for f of x and y basically with respect to the two variables. So in the direction parallel to the x-axis, now keep in mind that if we are allowing the input variable x to change, or we're looking at changes with respect to the x-axis, this is a key idea. To do that, if we're parallel to the x-axis, we must hold y constant. In other words, we can't be moving parallel to the x-axis if we are not holding the y constant. So here's what this might look like. So this is what a partial derivative looks like. We're going to take the limit as h approaches 0, and this with respect to x. Okay, limit as h approaches 0. We're going to have h in the denominator. We're going to have f of, now we had this fixed point, x naught, y naught, so x naught plus h, because we're allowing h to vary, comma y naught, minus f at x0, comma y0. This is very similar to what you saw back in Calc 1. Notice here that we have held the y constant. We are not allowing y to change. The only thing that's varying is the x component, or the x variable. And so this will actually give us our partial derivative with respect to h. Now, there is some notation that you'll need to learn how to use, and you will have to use. We call this the partial derivative of f with respect to x. Those are specific mathematical symbols that indicate a partial derivative. Or we can actually say f with a subscript of x. That's another way to indicate a partial derivative. And these are similar to what you saw back in Calc 1, where you had df dx and f prime of x. Now keep in mind that this partial symbol is very different than the df dx. So do not confuse this with df dx. They are completely different things. When I use the English letter D, it is implied. I am implying, or I am stating, that the function is a function of a single variable. And I know that this isn't the case because I was told I had a function of two variables. If I have a function of two or more variables, I must use that partial derivative symbol. Now there's similar limit notation for the partial derivative with respect to y. So our partial derivative with respect to y basically what we're doing here, and instead of allow variation parallel to the x-axis, we're allowing variation parallel to the y-axis. Allowing variation with respect to y-axis. And keep in mind this idea that we are thinking about the situation being parallel. So there's a similar definition. It's the limit as h approaches 0. This time we're holding x constant, and we're going to allow y to vary. So f of x naught comma y naught plus h minus f of x naught comma y naught all over h. Okay, so notice that in this particular case we are holding x constant, not allowing it to change. And so what we end up with here is another partial derivative. It's the partial of f with respect to y. Or I could use this subscript notation. I tend to not use the subscript notation as much because in contextual situations I find the other notation to be far more valuable for me to understand the situation that I have in front of me.